Now we're going to look at two-dimensional motion. Two-dimensional motion is motion in a plane. Motion in a plane. You can say maybe curved paths in a plane. Now, before we discuss this kind of motion, we need to define the motion variables we need, just like what we did in the case of one-dimensional motion. So let me start by defining the motion variables we need for this kind of motion. Okay, so the first one is called position vector. Position vector, we're going to use R to represent it. This is a vector whose tail is the origin, whose head is the location of the particle. This is a vector whose tail is at the origin, and whose head is at the location of the particle. The location of the particle. Okay, for example, let's say we have this coordinate system over here. If the particle is located over here, then what we call the position vector R is this vector. The vector whose head is origin and whose tail is origin, whose head is the location of the particle. This is what we call the vector R. Okay, now let's look at the components. The coordinates of this one are, let's say, x and y. Okay, so this one over here is the x component of the position vector, but it's simply the x coordinate. And this one over here is a y component of the position vector, which is simply the y coordinate of the particle. Okay, so for a position vector, the horizontal component is simply the x coordinate, and the y component is simply the y coordinate of the particle. Okay, and then next we have the displacement vector. Displacement vector, we're going to use delta r for that one. This is simply change in position vector of a particle. This is change in the position vector of a particle. Okay, we're going to use delta r, so this is simply the difference between the final location of the particle and the initial location of the particle. Now let's see graphically what this means. Suppose we have the following coordinate system. Okay, suppose this is, let's say, the initial position vector of particle. A particle displaced, let's say, from here to this location. Okay, so this is the final position vector, and this is the initial position vector. All right, now let's look at the difference between these two vectors. Remember, this vector minus this vector means this vector plus the negative of this vector. Now the negative of Ri is somewhere over here. That's the same magnitude and opposite direction. Okay, now if you bring the tail of this vector over here like this, so this would be the sum of Rf and the negative Ri, which is basically this vector over here. Okay, so this is what delta Ri is. It is the vector whose tail is the head of the first vector and whose head is the head of the last vector. So this is our delta R. This is delta R equals Rf minus Ri. So graphically, you can say the displacement vector delta R is a vector whose tail is the head of the initial vector of Ri, and whose head is the head of the final vector. The head of, basically, it's the vector that connects the head of the initial vector to the head of the final vector. Now let's look at the components of this vector. Now you see this over here is the x-coordinate of the initial vector. Now look, this one, this over here, from here to here, is the x-coordinate of the final vector. Now you see this one over here, which is the x component of the displacement vector, is simply the difference between the x component of the final vector and x component of the initial vector. You see this one over here, from here to here, is xf minus xi. So we can say that the x component of the displacement vector, which is delta rx, is simply the difference between the x of the final vector and the x of the initial vector. And we can do the same thing for the y component. You see, this one is yi, but the whole thing is yf, so this one over here is going to be yf minus yi, okay? So the y component of the displacement vector is simply y final minus y initial, okay? If you want the magnitude in the direction, the magnitude of the displacement vector will be square root of delta x, this are by the way delta x and delta y, so it will be delta x squared plus delta y squared, and the direction let's say it would be tan inverse of delta y over delta x, okay? Of course we would add 180 degrees if delta x is less than 0. All right, now let's look at average velocity. Average velocity, and we're going to use, this is a vector and this line means average. All right, so this is change in position vector per unit time. This is change in position vector per unit time. In other words, it is displacement per unit time, okay? That is displacement per unit time. All right, so mathematically, we can write this as this vector over here. Average vector is displacement divided by the time taken, okay? So its x component is going to be the x component of the displacement vector divided by the time, so that's delta x by delta t, and its y component is going to be the y component of the displacement vector, which is delta y divided by delta t. All right, so we have this for the x and y components of the velocity, and we have this for the x and y components of the displacement vector. Okay, next we're going to look at instantaneous velocity. Instantaneous velocity, again, is v for this one. Okay, now you can say this is velocity at a given instant of time, or we can define in terms of average velocity. You can say it's average velocity evaluated at a very small interval of time. So let's see the definition. This is average velocity evaluated at a very or infinitesimally small interval of time. Okay, so you take the average velocity by delta t, and then you take the limit of this as the time or the change in time approaches zero, that's what you call instantaneous velocity. Okay, so for the x component, you take the average, the x component, the average velocity, okay, and then you take the limit as delta t approaches zero. The same thing for the y. You take delta y by delta t, and then you take the limit as delta t approaches zero. Well, these are expressions of calculus. Don't worry about them. We're not going to deal with calculus over here. So basically, instantaneous velocity is velocity at a given instant of time. All right, and this is the way you write it in the language of calculus, but we're not going to deal with calculus in this class. And then we have average acceleration. Average acceleration. We're going to use the vector acceleration, and this line means average. Okay, this is change in velocity per unit time. Change in velocity per unit time. Per unit time. Okay, so mathematically we can say the average of this is the change in velocity divided by the time taken. Okay, or you can say v final minus v initial divided by delta t. Okay, so its x component is going to be the change between the x's, that is v final x minus v initial x divided by delta t, and the y component is going to be the difference between the y components of the velocities, vfy minus viy divided by delta t. Okay, so this would be the average accelerations. And of course, instantaneous acceleration is acceleration at a given instant of time. Instantaneous acceleration again is A. This is acceleration at a given instant of time, or you can say average acceleration evaluated at a very, very small interval of time. Average acceleration evaluated at a very, very small interval of time. Very, very small interval of time. Okay, so these are the variables we will need to discuss two-dimensional motion. We don't have to go beyond acceleration because our goal is to study the relationship between forces and motion, and force depends on acceleration. Okay, now we're going to specialize to a special kind of motion called uniformly accelerated motion. Uniformly accelerated motion. We have already dealt with this kind of motion in one-dimensional motion. It simply means motion with a constant acceleration. This means motion with constant acceleration. Okay, so it's a vector quantity. It means this is a constant, but when we write in terms of components, this has components ax and ay, so that means the x component is a constant, it doesn't change, and the y component is a constant, they do not change. That is both the x component, that's the rate of change of the horizontal component of the velocity with time, and the rate of change of the vertical component of the velocity with time, they're all constant. So now we want to look at the equations of motion of a two-dimensional motion. Now, first let's note that the vertical motion and the horizontal motion are independent of each other. Okay, what that means is acceleration in the horizontal direction does not affect motion in the vertical direction. Okay, and acceleration in the vertical direction does not affect motion in the horizontal direction. What that means is we can treat the x components, the x motion and the y motion separately. Okay, so that's what we're going to do. Let's separate between x motion and y motion. Okay, now the x motion is a one-dimensional motion. Okay, and the y motion is also one-dimensional motion. So what that means is we can use equations of a one-dimensional motion for this kind of motion. Okay, now the only difference over here is we're going to distinguish between x and y components. So we're going to write the same equations, we use it for one-dimensional motion, but we're going to distinguish between the x component and the y component. All right, so let's write these equations. We have vfx equals vix plus x component acceleration times time, and then we have delta x equals bixt plus half ax t squared, and then vfx squared equals bix squared plus 2a delta x, and then we have delta x equals vix plus vfx over 2 times time. So these are the equations for uniformly accelerated motion in the x direction. We're just using the equations for one-dimensional motion, but we have to specify this is for the motion in the horizontal direction, so that's why we have the subscript x everywhere. The same thing for the y. The only difference is we use now y instead of x, so you've got vfy equals biy plus ayt delta y equals biyt plus half ayt squared, and then we've got vfy squared equals biy squared plus 2a delta y, and then we've got delta y equals biy plus vfy divided by 2 times time. Okay, so these are equations that govern the x component of the motion. These are the equations that govern the y component of the motion. But we're mainly interested in motion under gravity, which we will call projectile motion. Okay, so let's specialize to projectile motion. Projectile motion is a very good example of a uniformly accelerated two-dimensional motion. Okay, so we're going to specialize to projectile motion. Projectile motion. This is curved motion under gravity. This is curved motion under gravity. Okay, what happens if you throw an object horizontal? It's going to go something like this. Okay, something like this. Okay, that's what you call a projectile motion or two-dimensional motion under gravity. Okay, now let's look at the acceleration due to gravity. Okay, the direction of acceleration is downward, and it doesn't have an x component. Okay, is downward, so it doesn't have a horizontal component. So we know for this kind of motion the x component of the acceleration is 0, and the y component we have already saw in the case of one-dimensional motion. Its value is negative 9.8 meter per second square. Okay, it's negative because its effect is to decrease velocity, and as you remember, we customarily use g for this value, for negative 9.8 meters per second square. Okay, so all we're going to do is we're going to replace ax by 0 and ay by g to get equations of a projectile motion. Okay, so let's write the equations of projectile motion. equations of a projectile motion. Projectile motion. Okay, so we're going to put ax equals 0 for the x motion. Let's write the x motion on this side. For the x motion, we're going to put ax equals 0. You see, when you put ax equals 0, you just get vfx equals vix. Okay, so the first equation is vfx vix. What does it mean? The horizontal component of the velocity is a constant. There is no acceleration horizontally. Okay, so the x component of the velocity is not going to change. It's always the same. For example, let's say you throw a ball horizontally with a speed of 10 meters per second. Okay, the object will keep falling because the y component is changing, but the x component of the velocity will not change. Even by the time it hits the ground, the x component of this velocity will still be 10 meters per second. So the x component of the velocity is a constant. It doesn't change during the motion because there is no acceleration in the horizontal direction for acceleration. Now let's do the second one. If you put ax equals 0, you get delta x equals vix times t. Okay, so you got delta x equals vix times t. This is the equation of a uniform motion. You see there is no acceleration, so it's basically distance equals speed times time. Okay, in the x direction. All right, now we can do the same thing to the other two equations, but we're going to end up with the same redundant equations over here. Okay, so these are the only two equations we have for the x motion of a projectile motion. Now let's look at the y motion. Okay, in this case we're going to replace ay by gravitational acceleration g. This was ax equals 0. All right, so over here we get vfy equals viy plus gt. Okay, so let's write the equations. So you got vfy equals viy plus gt. Now our displacement is going to be delta y. Okay, so you've got delta y equals the y component, the velocity, plus half gt squared. And then we have vfy squared equals viy squared plus 2 times acceleration times the displacement, and then of course we have delta y equals viy plus vfy over 2 times time. So these are the equations we can use for projectile motion. Okay, so the horizontal motion is a uniform motion because the acceleration does not have a component in the horizontal direction, and this is a uniformly accelerated motion in the vertical direction. Okay, now let's look at this variables now as a typical motion. Suppose let's say a bullet is fired from this building with this velocity. Okay, so this is the velocity. Let's say this is going to be the initial velocity, right? So this is the initial velocity. Let's say the angle over here is vi. Okay, so what's going to happen is they will go up and then eventually will fall. So what's going to happen. Okay, so this is our initial velocity. So this over here is the x component of the initial velocity, and this over here is the y component of the initial velocity. So if you know the angle, you can calculate this with the following. Vix is vi times cosine of theta I, and viy is the speed times the sine of theta I. Okay, all right, now let's look at the displacement vector. If you remember, the displacement vector is simply the vector that connects the initial location to the final location. Okay, so this is our delta r. This vector over here is delta r, the vector that connects the initial location to the final location, delta r. Okay, what are the components of this vector? These are its components. This is its x component, delta x, and this is its y component, delta y. So delta x and delta y have nothing to do with the distance traveled by the particle. They're simply the x and y components of this displacement vector, and that vector is simply the vector that connects the initial point to the final point. So delta x is the horizontal component of this vector, and delta y is the vertical component of this vector. And remember, don't forget this sign convention. If the y is decreasing, it's going to be negative. All right. Okay, and then we have the final velocity over here. Just before it's the ground, this would be the velocity over here. Okay, so this would be the final velocity. Let's say this angle is theta f, and then we have these components. This is vfx over here, and then vfy over here. So you can calculate them like this. Vfx is vf cosine of theta final, and vfy is vf the sine of theta f. Okay, so these are the variables we need for this kind of motion. From the magnitude direction, we get the x and the y components of the velocity, and to find delta x and delta y, we simply connect our initial point to the final point. Its horizontal component is delta x, its vertical component is delta y. All right, so now we're going to look at some examples. Example. Now suppose, let's say a bullet is fired horizontally from a 20-meter tall building like this. Okay, it's fired horizontally, let's say with the speed of maybe 100 meters per second. Okay, so that's our initial speed, and it's fired horizontally, so that's what's going to happen. It's going to fall somewhere over here like this. Okay, so we're going to ask some questions. A, let's say, how long does it take to hit the ground? To hit the ground. Okay, your initial point and your final point depend on the question. So in this case, you see, the time is from here to here. So this is my final point, this is my initial point. Okay, and that means this is my displacement vector over here. This is my displacement vector over here, delta r. So this is going to be my delta x for this problem, and this is going to be my delta y. Okay, so let's write what we know. We know the initial speed is 100 meters per second. Okay, we also know the direction because it's horizontal. What's the angle for horizontal? The default angle for horizontal, which is east, is 0. So theta is 0. So from this information, we can calculate the x and the y components of the initial velocity, which we'll need in the equations, right? So you've got vix is vi cosine of theta I, which is 100 times cosine of 0 equals 100 meters per second. Okay, and viy is vi, the sine of theta I, that's 100, sine of 0 equals 0. This is 3, but you don't have to go through this. It's horizontal, so it's not going to have a vertical component, and the horizontal component is going to be itself. Now, what else do we know? You see, this is the displacement, okay? And we know the magnitude of that is 20 and it's going downwards. So delta y is negative 20. That's what we know. It's negative because y is changing. Okay? So our goal is to calculate time, the time taken from here to here. Alright? So all you have to do now is go back over here and select the suitable equation. Okay? If you look at this equation, we have already concluded that VIY is 0, right? So G is a constant, so we can calculate time from this equation. Okay? So let's use that equation. We have delta y equals VIYT plus half g t squared. Okay, so this is negative 20, VIY is 0, it's over here, and then this is negative 4.9, but let me use approximately negative 5, okay, but you always have to use 9.8 t squared. Okay, so we have t squared equals 4. Time is always positive, we should take the positive square root. So the time taken is 2 seconds. Alright. Now B, let's say how far horizontally did it fall? Did it fall? Okay, so in this question we're looking for delta x. Okay, that's what we're looking for. Now there's only one formula for delta x, and that is delta x equals VIX times the time. Okay, so we have already obtained these numbers. VIX is 100, VIX is 100 meters per second, and the time we just calculated to be 2 seconds. Okay, so the horizontal displacement is 100 meters per second times 2 seconds, 200 meters. So the bullet will fall 200 meters away. Okay, now C, let's say calculate the horizontal component of its velocity just before it hits the ground. Okay, so now we're looking for the x component of the final velocity. That's the velocity at the final location. We're looking for this velocity. Okay, so we're being asked for this component over here, which is the x component of the final velocity, VFX. That's what we're looking for. Okay, so if you remember, the x component of the velocity does not change. Okay, see, the velocity remains the same. So that's it. We have VFX question mark, but VFX equals VIX, but we already know the VIX is 100 meters per second. That's it. D, calculate the vertical component of its velocity just before it hits the ground. Okay, now we're looking for this one over here. That's what we're looking for now. Okay. So for VFY, if you look at the equations, we can use this equation. We know VIY, we know the time, so we can use that equation. Okay. So we're looking for VFY question mark, and then we have VFY equals VIY plus GT. But we have already calculated VIY is 0. The initial velocity does not have a y component, you see over here, and the time is 2 seconds. So this is 0. I'm going to use approximately 10 for gravity times 2. That is negative 20 meters per second. Why is the velocity negative? Because it's going down. Okay, just before it hits the ground. All right. Now we can consider a case where the bullet is fired from the ground. Okay, so it's the ground. Let's say the bullet is fired like this. Let's say the velocity is still 100 meters per second, and this angle is, let's say, 37 degrees. Okay, so what's going to happen is it will go like this, and then eventually we'll come back to the ground like this. Okay, so let's ask some questions. A, let's say, how high would it rise? How high would it rise? Would it rise? Okay, now it's the problem that determines your initial and final point. So we're talking about this point over here. Okay, so this is my final point, this is my initial point. Okay, so my displacement vector is this one. My displacement vector is this one over here. This is my delta r. What that means is this one over here is my delta y, and that's what I'm looking for. Okay, so the question is delta y, how high? Okay, now let's write what we know. Of course, we know we have information about the initial velocity. So the initial speed or velocity 100 meters per second, and the direction is 37 degrees. Okay, so out of this we can calculate the x and y components of the initial velocity. So you've got Vix equals 100 cosine of 37, which is going to be 80 meters per second, and then Viy is going to be 100 sine of 37, which is going to be about 60 meters per second. Now let's see what we know over here. The velocity is tangent to the trajectory. Okay, so over here at the maximum height, the velocity is horizontal. Even though we don't know its magnitude, we know it's horizontal at the maximum height. That means its direction is 0 at the maximum height. So I know theta f is 0. Okay, what does this mean? Vfy, which is Vf times sine of theta f, is 0. You see, Vf sine of 0 is 0. So in other words, the velocity doesn't have a vertical component at the maximum height because it's horizontal. So what we know is Vfy is 0. Okay, so from this information now we have to calculate delta y. And now let's look at our formulas. You see, if you look at this equation, I know this one, Vfy is 0, I have this one, so I calculate delta y from this equation. Okay, so we have Vfy squared equals Viy squared plus 2g delta y. Okay, Vfy is 0, Viy is 60 over here, plus 2, I'm going to use approximately negative 10 for gravity, delta y. Okay, so you've got negative 3600 equals negative 20 times delta y. Okay, so delta y equals 3600 over 20, that is 180 meters. Okay, that's how high the bullet rise. All right, now let's ask another question. B, how long does it take to reach the maximum height? The maximum height. So we're looking for the time to reach the maximum height. Maybe we'll call it T max over here. Let's look at the following question. Vfy equals Viy plus gt. Okay, so the y component, the velocity, the maximum height is 0. This one is 60. This is minus 10t. Okay, so we get negative 60 equals negative 10t, or t equals 6 seconds. Okay, so it takes 6 seconds to reach the maximum height. All right, now let's see how long does it take to return to the ground. To return to the ground. Okay, now the motion is symmetric. If it takes 6 seconds to go up, it's going to take 6 seconds to come back. So it should be 12 seconds. But let's do it this way. Now, this is our final point now. Okay, so my displacement is this one over here. It's horizontal. So you see, my displacement does not have a change in y. The change in y is 0 because this and this are at the same height. Okay, so what we know in this problem is delta y is 0 for this problem, because the displacement is horizontal, it doesn't have a y component. Okay, now if you use this equation, delta y equals Viyt plus half gt squared. Okay, you got 0 over here, and then Viy 60 times t is approximately negative 10, so it will be negative 5 t squared. Okay, so you've got you can divide by t. We have 5t equals 60 and t equals 12 seconds. Okay, but you have to go through this because the motion is symmetric. If it takes 6 seconds to go up, it takes 6 seconds to come back, so it's going to be 12 seconds. Okay, now let's say calculate the x and y components of its velocity just before it hits the ground. Okay, so in this problem, this is what we're looking at. The velocity just before the ground is like this. Okay, so this is my Vfx and this is my Vfy. All right, that's what I'm calculating. But as you know, Vfx is easy to calculate because the x component of the velocity does not change. Okay, so the question is Vfx question mark Vfy question mark. Okay, so Vfx equals Vix, which is 80 meters per second. Okay, for Vfy, we can use this equation Viy plus gt because we know the time is 12 seconds, okay? And VIY is 60, so you've got negative 10 approximately, and this one is 12, okay? So you've got 6 minus 120, negative 60 meters per second. Why is it negative? Because it's going down. All right. Finally, let's look at one example. Let's say it is the bullet is fired from a building. Let's say with again 100 meters per second. Let's say this angle is 53 degrees. Okay, so it's going to go like this. It's going to go like this and come back to the ground like this. Okay, let's say this, once again, let's say it's 20 meters. Okay, now let's say A, calculate the components of its velocity just before it hits the ground. Okay, right over here. So this is the velocity, so we're looking for this Vfx and Vfy. Okay, so let's write what we know. The initial speed is, we're looking for this question mark, Vfy question mark. So this is 100. The direction is 53 degrees. Okay, so from this you can get Vix equals 100 times cosine of 53, which is 6 meters per second, and then Viy equals 100 times the sine of 53, which is about 80 meters per second. What else do we know? You see, this is my final point, my initial point, so this is my displacement vector delta r. Okay, so this is its horizontal component delta x, and this is its y component delta y. Okay, but we're given this one is 20 meters, and it's going down, it's going to be negative. Okay, so you've got delta y equals negative 20 meters. So that's what we know. Okay, so let's solve for the velocities. Now Vfx, as you know, is always equal to Vix, and we just calculate Vix to be 60, so that's easy. It's 60 meters per second. For Vfy, let's use the following formula: Vfy squared equals Viy squared plus 2g delta y. We know delta y, we know Viy, so we can calculate Vfy squared from here. Okay, so you've got Vfy squared equals Viy is 80, so you've got 80 squared plus 2, gravity approximate negative 10, and delta y negative 20. Okay, so we have 6400 plus, this is going to be positive, negative times negative, and that is 400. So that is 6,800. All right. So Vfy, mathematically, the answer will be plus or minus square root of 6,800. Okay. So which one do we pick, the plus or the minus? We know the direction of the final velocity before it's the ground is downward, which means we have to pick the negative sign. So it's the negative of 6800 meters per second. That's negative 10 square root of 68. square of 68 is a little bit above 8, so it's 80 something meters per second. All right. Now we can say, we can calculate the time taken calculate the time taken to hit the ground. So once again, you can use, we're looking for time, we can use this formula, BFY equals BIY plus GT. Okay, we just calculated BFY to be negative 10 square root of 68 equals BIY. BIY is I think 80 meters per second. Okay, so you've got 80 and this is minus 10t. Okay, so we have negative 10t equals negative 10 square root of 68 minus 80. So t would be whatever this number is, 80 plus 10 square root of 68.